All right, how we sketch a graph. We're looking at sketching inverse cos graphs, inverse sine, inverse tan. My advice, as I've stated before, is rearrange the equation in a form that lets you easily see the transformations that have been applied. That is a number one imperative thing. Now, I've got a fair few here. This would be as hard as it gets. In other words, if I had 1 minus x, that would not allow me to see that there has been a reflection in the y-axis. Now, it's important to note though, let's note what has happened for this graph. Well, first of all, we can say that there has been a reflection in the y-axis. Now that's over here, of course. And we also have a reflection in the x-axis, don't we? Now, what's also happening? What's happening with that 2 at the front? There's a dilation. Dilation parallel to what axis? Parallel to the x-axis, yes. Up and down though, of course. So we're looking at dilation this way of 2, isn't it? What about where this negative sign was? What happens if there was a 2 out of there? What would it be? Would it be a dilation? Well, it would be, but dilation by a factor of, would it be 2? It would be a half, wouldn't it? It'd be getting thinner. And let's think about it. What's happening to the period if 2 pi on n? Okay, so 2 pi on n, 2 pi divided by 2 would be a half. So it's being dilated by a factor of a half if that was a 2 there. That's the important thing to notice. To be honest, a lot of the time that's not going to change too much. A lot of the time the values that in your graph that are going to change it are that. There's going to be some fattening or thinning though, however, with this value here. All right, so we've applied that dilation of a factor of 2 parallel to the x-axis. And what else is there? We've got translate 1 unit to the what? 1 unit to the right. And then we've got to deal with 3 units up. So let's go. Now what I was saying is sketch the base form first. In other words, we have, and with the endpoints is important because of course those endpoints are going to be doing some dancing around, aren't they? We don't give a hoot what all of these other points are, which aren't sort of nice round things such as 1 and pi. So it's important to get the endpoints down pat, which we've done. There you go, -1 pi, 1, 0. Let's start applying some of these transformations though, shall we? And some of these transformations is, well, the graph of y equals cos of, I'm going to do the reflection in the y-axis first, which means that this shape here, reflected, becomes this shape, doesn't it? And if something's reflected, because I've got the points -1 pi over here, then that x coordinate must be positive, so it becomes 1 pi. You can see that I've done it there. I've done it here. Let's apply that first. Okay, now we've done that. Let's reflect in the x-axis. So therefore, stage 3, we can say, okay, let's reflect in the x-axis, which means there becomes there, and it's going to look like something like this. And this -1, 0 is going to stay exactly the same, isn't it? And this thing over here is going to be not 1 pi, or it's going to be 1 -pi. Happy with that? Okay, dilation a factor of 2 to the x-axis. Now, that's this thing, but what that means is that all the y values are multiplied by 2. So 0 divided times 2 is just, nothing's going to change there. But what we do know is that this is going to be, this is going to be -1, 0, and this is going to be 1 minus 2 pi. Oh gee, that's a terrible, it doesn't look like that. God, what's going on with me? All right. Okay, let's just say there we go, that's looking a little bit better. It's minus 2 pi. Okay, we now have got our endpoints. Now, the good thing about having that graph and dealing with the endpoints as we go is now I've got to, if you think about it, the endpoints are going to move across and to the right some. So we've got now moved 1 unit across. So that negative 1, 0 becomes 0, 0. Okay, and we then go to negative 2 pi. So it's going to look something like this. To negative 2 pi. And that's 0, 0. We've dealt with that now, and then we're moving 3 units up. So now we're looking at the graph, our final graph. Our final graph is going to look something like this. 3 units up. So let's say 3, 0. Is there going to be... Is there going to be an x-intercept? Is there going to be an x-intercept? Yeah. Because that's, negative 2 pi. But we can say that that's 3 up is 1. 1, negative 2 pi. Negative 2 pi plus 3 it's going to be, isn't it? 3 minus 2 pi is a negative value. So this is still going to remain as 2, and that is going to be 3 minus 2 pi. There we go, we're done. Now, of course, we've got to find the intercepts. We'll get to that stuff later, but does that make sense? So that's, sorry? Oh, yeah, bad. Yeah, my bad, 0, 3. X comes at 4y. I've got to go to Preppy to learn my ABCs. All right, now, I'll be honest with you, that's ever as hard as it gets. Would you ever have to do even one with that many transformations? No, but if you can do that one, if you can follow me with that one, you can draw any of them. Okay, so let's have a look. And, okay, well, that's a cosec graph. I don't want you to sketch that. Let's have a go at this one, ladies and gentlemen. By the way, this is on the formula sheet. Sketch the graphs of this. So this is what the formula sheet will give you. Have a go at this. I'll pause it and I'll go through with you to make sure. So test yourself now. See if you can do this one. We went through... Resume. So we've got to get it in the base form first, otherwise we're not going to be able to apply all of these transformations. Get it in the base form, and of course we need to know what it looks like. Of course, the formula sheet would tell me, I don't want that. The formula sheet would tell me that inverse sine, has a range of minus pi on 2 to pi on 2. So importantly, let's get the endpoints there. Minus pi on range, it has a domain of negative 1 like so. So, if we are applying a dilation of 2 out the front here, then what does that mean? That all the values of y we multiply by 2. So I'm going to apply that first. So the graph of Nick off you. The graph of 2 sine, inverse sine of x is going to look like this. Same shape, same everything. But that is 1, and that is pi. Yes? No? Maybe? Like so. So now what we do is, now what about what's going to happen here? The dilation of a third of parallel to the y-axis. So which values am I dealing with? It's getting thinner, isn't it? So that 1 becomes what? What is that? Does that change? One over 3, isn't it? Yes. So the graph of 2 inverse sine of 3x is going to look like this. It's going to thin out, isn't it? It is going to get much sort of thinner. Okay, and the end point there is going to be 1/3. That pi is not going to change though, is it? Pi. All right, negative a third. Negative pi. Okay, I think we've now dealt with the worst of it. Because now what I want to do is I want to translate 2 units, 2/3 units to the right. So we've got our 2 translations and we're done. Translate 2 units right, 2/3 units right, and pi up. Let's pi up. Sounds like we could be a superhero. Let's pi up. All right. So 2/3. So that 1/3, ironically, 1/3 becomes 1 again, doesn't it? That's quite nice. Doesn't always work out that nice and friendly, but yeah. And so it's back to 1 pi. But that negative 1/3 is 1/3, isn't it? We're adding 2/3. So that's going to be 2/3. Is there going to be a y-intercept in this case so far? I don't think there is. So we've got 2/3 negative pi. Let's just say that that's there, ladies and gentlemen. All right, we now have our shape and it's a lot thinner than it was before. Something like so. We're now translating pi units up. So let's add pi to everything. So I'm going to say that that's 2/3. Oh my goodness, look at that. Look at that. You know what? I'm not even going to bother. I'm just going to draw the axis again. How's that sound? 2/3 negative pi becomes 2/3 0. And that is 2 pi. Is that what you got? So we've got a graph. Now then, of course, and when you deal with these, don't go finding x-intercepts or whatever. Shh, get the shape right. Get the shape right, because in this case we know that we don't have to bother looking for a y-intercept. We can just look for an x, and then we don't even have to do that, because with transformations we know that the x-intercept is equal to 2/3. Yeah, well, sorry, 1/3. We've moved it across 2/3. I did have that over here. That negative a third plus 2/3 is equal to 1/3, yes. Okay, so that's it. And of course, if I was to sketch that graph, we could also check. And look, very rare, you're not going to be asked to sketch a graph like that in an exam 2. It's an exam 1 question. So now just quickly, 2 trig inverse sine. Calculator recognises it as that 3x minus 2 plus pi. Can you please have a go at the exam question, which is on R cos 1? It's towards the end of the sheet, please. Have a go at that. It's there. Now, as you can see, it's very hard to do it. It's very hard. So just quickly with this one, if I'm trying to find the domain and range, we know that x is between 1 and -1, don't we? That's if that was x. So if I replace x with 1 minus 2x, the best way I think to do it is like so. Now we've just got to solve this inequality. So we solve this inequality. I'm going to subtract 1 from both sides, which is going to give me -2, -2x 0. And then I'm going to divide both sides by -2. Is that the answer? Is that the answer for the domain of the... Yes. 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 Hallelujah. Is that right? Okay. That is right. It's just that I'm dividing -2 by -2 is 1, isn't it? Thank you. All right, so that's how I would do it. You don't have to sketch graphs. Don't have to sketch graphs in order to do that one. Now, of course, the range... Well, what am I doing? I've got... I do know that... Is the range going to be affected, though? Isn't there... If I was to put out a 2 out the front, a -2 out the front, inverse cos of -2, and that's x minus a half. There's a translation 1/2 units to the right. What would be the range in this case? What would be the 0 to pi? Same thing, because of course there's no dilations parallel to the x-axis. So therefore, yes, if you understand the transformations, and the range is equal to 0 to pi. Now, of course, that also helps us a fair deal with sketching the graph too. My range is 0 to pi. That is 0 to 1. Inverse cos, though, we know, is an inverse cos, it's going to be up there. So if that's going to be, isn't it going to look something like this? Yes, no, maybe? No, I don't think so. Because we've got to, what have we got to do? Don't we have to reflect in the x-axis? Y-axis, x-axis? Is there a reflection? Is there a reflection? No. There's not. Is there? 1 minus 2x. So how would you change that? What would you do? You would say it's a reflection in the y-axis, isn't it? So let's have a look at what the domain and the range is. So that's what you should have got, something that looks like that. Don't worry about finding the gradient. All right, I wanted to, before we go, I wanted to go through this question. Now, importantly, have a go at this question, please. All right, I'm going to do this as quickly as I can. How does that sound? Just remember that you can't do cancelling, can you, when you're solving trig equations? So I've got 2 cos of x is equal to root 3 cos of x over sine of x. Never, ever, ever do this, ever. You can't. So let's get it onto one side, and I'm going to do cos of x as a common factor. We have 2 minus root 3, what is it? 2 minus root 3 on sine of x is what, equal to 0. Okay, good. So therefore we've got 2 things. We've got cos of x is equal to 0, and we've got 2 minus root 3 on 2 sine of x. So therefore we've got sine of x equals what, root 3 on 2? Okay, now you might go, hang on a minute, this isn't that bad, 3 marks. This is one of the worst done questions ever. Because what can you tell me about the question? Have they given us a domain? No, they have not. So we're going to have infinite amount of solutions, aren't we? Okay, it's really important. Find all real solutions. So, just quickly, now we know cos of x equals 0 at pi on 2. Negative pi on 2. Yes? Pi on 2, negative pi on 2, etc. Okay? What am I doing though? I'm adding pi, aren't I? Yeah. So therefore we can say that our solution is, one of our solutions is x is equal to pi on 2 plus k pi, such that k is an element of z, integers. There you go, don't go anywhere. No, hang on, wait a second, thank you. Same thing, this time where does sine of x equal root 3 on 2? Sine of 60 pi on 3. So we can say that x is equal to pi on 3 plus 2k pi. K is an element of z. And the last, we also have to deal with x is equal to 2 pi on 3 plus 2k pi. Okay, 3 marks. That was actually really poorly done exam question. And that's solving trig equations. That was one of the harder ones. If you can do that one and understand that, I think you're fine. Thank you very much.